Well, thank you for that wonderful introduction. I'm actually here on a mission tonight. I want to try and change your perspective. I hope that you will leave here tonight with a more cosmic perspective than perhaps you entered. This is something that Arthur Clarke had in abundance. Visiting his home in Sri Lanka and looking at all his telescopes and all of the many projects that he was so enamored of, he had this larger view. He saw ourselves in a bigger picture than most of us do during the day. So, I'd like to invite you to think about here and now in a larger perspective, in a larger context. So here, okay, it's really simple. We're here. We're here in the Sydney Harlan auditorium. We're here on F Street. We're here in Washington, D.C. And from low Earth orbit, we would understand ourselves as being here on the eastern seaboard. Since 1968, when Bill Anders took this image of Earthrise as he was coming around the limb of the moon in Apollo 8, we've been able to understand ourselves as a whole world floating in space. And a few years ago, I hope you got the memo, the Cassini spacecraft, which was studying Saturn, turned around and looked homeward and saw us here. At the end of that arrow, there's a little white dot, and we're all on it. So we sent a memo. We hope you went out on the lawn and waved to Cassini during this selfie. But this is an amazing image of where we are in space. And before that, as the Voyager 1 spacecraft was leaving the solar system, it turned around and looked home and saw this pale blue dot caught in a beam of light and dust. And that's us. We're here on the edge of a very large galaxy where our star, the sun, is only one of 400 billion other stars. And no, that's not a real picture of the Milky Way. Nobody can get outside and take that picture. That is a picture of a galaxy that we think looks very much like our own. And of course, that galaxy is one of something like 200 billion galaxies in the observable universe. And this beautiful image from the Hubble Deep Field shows us those galaxies in abundance. Each of those points is not a star, it's a galaxy full of hundreds of billions of stars. And you'll note that some of those points are smaller and fainter because they're farther away. And that reminds us that because of the finite speed of light, as we look farther away, we look back in time. And so we now have to think about now, right? Now, 13.8 billion years of cosmic evolution following the Big Bang. We are in an era of stars and galaxies and planets that is far different than the universe was earlier in its evolutionary phase. So this idea of time, all right? And where do humans trace their origins? Well, we trace our origins not just back through the centuries of our families, and not just back through the millennia of our architecture and our art and our many different experiments with governance, not just back through the millions of years since humans branched off from the great apes, not just back the 2.4 billion years that Earth's atmosphere has been perfused with oxygen thanks to the labors of photosynthetic algae. And not just back to the origin of the solar system 4.5 billion years ago, but back a few 100 million years earlier to a cloud of gas and dust and molecules that was polluted by the emissions from stellar explosions, supernova that left remnants such as this beautiful modern supernova remnant, remnants that polluted the molecular cloud with all the stuff that makes you, and all of us and our world around us. Because the calcium in your bones, the iron in the hemoglobin molecules of your blood, they were all fused, they were all cooked up deep inside the core of a massive star that exploded, leaving behind these remnants, these pollutants for that molecular cloud, which was to condense into the sun and the planets and our solar system. Just as this current remnant will influence the cloud in which it lives, and that will collapse into future generations of stars and planets and perhaps life. Because it's really true that you and I and all of us are intimately connected with these long ago times and far away places. Carl Sagan told us, and he was absolutely, completely right. We are made of stardust, and it takes a cosmos to make a human. Now, it's taken scientists a millennia to figure out this pathway from the molecular cloud to life as we know it on this planet. And we are curious to know more. We want to understand why we're here. Where specifically did we come from? Where are we going? And of course, who else is out there? So I've spent my career on this search for extraterrestrial intelligence. And I'd like to say that it's given me an opportunity to talk to many audiences like you. And I think that SETI has something very important to do, even before, or even if we never detect a signal. Because if you think about it, and think about life beyond Earth, then it's like holding up a mirror to all of us on this planet and saying, you know, compared to something else out there, you're all the same. You're all Earthlings. And it helps to trivialize the differences among us. And it's really important to do that. It's really important to get the whole world involved in this search for life beyond Earth. Because if we learn to cooperate on that venture, then that builds a very strong framework for global communication, global cooperation on these other huge challenges that we face. Global climate change, water security, food security, poverty, all of these challenges that we need to find solutions for, and these challenges that do not respect national boundaries, these problems that have to be solved globally. And that's why I think it's so important to have this larger perspective, this cosmic perspective, to truly see ourselves as Earthlings and move forward as if we really meant it. So my last word actually belongs to Caleb Scharf, astrobiologist at Columbia University. And Caleb reminds us that on a finite world, A cosmic perspective is not a luxury, it's a necessity. So I'd like to give you a little homework assignment. All right, when you get back to these wonderful mobile devices, I challenge you to go change your personal profiles so that the very first thing about you that you say is that you're an Earthling. And then, damn it, go act like it. Thank you.
You can, and I'll come out.
Well, let's have some, can we have the lights up and have some questions? I promised I would be very short, and I am short. So we do have time for questions, and I'd love to hear what you're interested in. Oh, I thought you were going to the microphone. Okay, anyone? I won't bite. Yes.
Can you tell us if the SETI for everybody is available and if security is not a problem?
Okay, so I think you're asking me about a screensaver called SETI at Home, which was developed at UC Berkeley about 12 years ago. Yes, it's still running. It's now analyzing data from the Arecibo Observatory in Puerto Rico and the Green Bank Telescope in West Virginia. So if you want to participate in this analysis, you can download this screensaver, and when you're not using your computer or not using it very heavily, it will process the recorded data and look for signals. There is, to the best of my knowledge, no security. I mean, there have been literally millions of people who have been using this very successfully. I think it actually was the thing that put distributed computing and citizen science on the map, right? Didn't invent it. People had been putting computers together to factor Marcine primes or to try and break codes. But this application was so sexy that everybody jumped on board, and now citizen science is a wonderful asset to all of us who are trying to answer problems that are large and small but require a lot of data analysis that we can't do by ourselves. And so you can fold proteins for cancer research, you can look for and identify animals in camera traps all over the world, you can count craters on various bodies. You can do all kinds of things with citizen science, and I encourage you to do it. So, yes, there's the hand here.
If you were to make contact with a non-Earthling, have you thought about the first question you would ask?
Well, yeah, actually, that one already showed up in the film, right? So my question would be, how did you survive the technological adolescence that we seem to find ourselves in today, with all of these challenges and problems that technology made, and problems that technology is going to have to solve? How did you make it through? How did you get to be an older, stable, technological civilization? Because that's the future I'd like to see for us. All right, there's a hand in the middle there.
About a year ago, there was a highly unusual star system with a very strange spectral emission that you couldn't discount, let's say, dust or planets or something like that. It came up in the mainstream media. That was very intriguing. I was wondering if there's been any follow-up, and taking a look at that, and what are the tool sets that we have now that we can look at those things? I thought it was a nice sphere.
Okay, so I think you're talking about Boyajian's star, or the WTF star, right? Where's the flux? This is a star that was detected in the data from the Kepler spacecraft, which was looking for planets orbiting other stars. And the technique it used was to look for those moments when the planet passed between the star and the Kepler telescope and dimmed the light a little bit, because that dark planet shadow makes the luminosity of the star just a little bit smaller. And then you look and you find it, and then you look again, and that might be a period, and you look to see if it happens a third time and a fourth time, and now you've got a planet. Well, this star didn't dim by a little bit, a percent or less, but it dimmed by 20%, huge, and it didn't do it periodically. So in fact, the Kepler spacecraft didn't find this planet, didn't recognize this star. It was citizen scientists who were looking by eye at the Kepler data that said, what's this? And so it's very hard to come up with an explanation for this behavior, because if you think about dust being the thing that obscures the intensity of the star, dust from comet tails or something that wouldn't be periodic, it's very hard for that dust not to heat up. And if it heats up, you should see it in the infrared, and we don't. So there's a long litany of things we've tried to map the observations with some natural explanation. And at the end of that, people say, well, maybe it's a megastructure. Maybe it's somebody building something like a Dyson sphere. But that's actually the answer of last resort. And so what we've done is there have been a lot more observations of this star as new events happen. And indeed, the spectroscopic appearance, the way this material looks at different wavelengths, we think it's going to end up being dust, a natural explanation. So we don't have to invoke astroengineering, although that might be an interesting answer. But we're still working on the natural one. Okay. Somebody's pointing, but I can't see. Oh, all right, there's a hand there.
Yes, Douglas Adams, in The Hitchhiker's Guide to the Galaxy, said that the entry for Earth was mostly harmless. And I was curious what The Hitchhiker's Guide to the Galaxy, Douglas Adams' work, has meant to you.
I think he's fantastic. I love, wonderful science fiction and science humor. And you might be interested to know that the Allen Telescope Array in Northern California that we have built to look for evidence of radio signals from extraterrestrial technologies happens to have 42 telescopes. I'm sorry, I didn't repeat the question. I was asked about the influence of Douglas Adams and his work on SETI and on my career in general. And so yes, we wanted 350 telescopes, but we didn't have enough money. And so having to stop somewhere less than 350, I thought 42 was a pretty darn good place to stop. Life, the universe, and everything.
We have time for one more.
All right, I see a shirt there, the white shirt.
In your career, how has school children's responses and thinking about your ideas changed? Have you seen it change through time? How kids think about it?
Well, the question is, have we seen any change over time, over my career, in students' reactions to this idea? I have to say we've worked very hard to try and shape those reactions. We have developed, with funding from the NSF and NASA, curriculum materials, both add-on materials that a teacher can do to do hands-on and minds-on experiments, adding those to curriculum that already exist, as well as a 9th grade curriculum which is cross-disciplinary, interdisciplinary, called Voyages Through Time. And we have seen fantastic reactions because the theme is so intriguing. Kids still like ghosts and creepy crawly things and E.T. And when you build a science curriculum around the arc of a story about our place in the universe and the potential for others, kids just eat it up and the science goes down without even noticing. So it's been great, and we want to see more of that. Thank you.